So now we know not only that the first order of business is to make the system stable, meaning it shouldn't blow up, it should behave well, but we also know what this means, namely that the eigenvalues of the system should have negative real part. And even though we saw some critically stable cases last time, including a rather awesome set of robots slamming into each other, we typically don't want critical stability. We want asymptotic stability, which means that we need to have strictly negative real part of all the eigenvalues here. And today we're going to actually achieve that, or try to achieve it, by designing a controller. Because remember this picture. We have our system, x dot is ax plus bu, where u is the input, and then y is equal to cx. So whatever we do to our control choice has to depend on the things that we have access to, which is y. We don't know the state of the system, but we certainly know the output. So today, we're going to try something called output feedback, which means we're going to take the output of the system and use it and feed it directly back in as a way of controlling it. And we're going to start by returning to our old friend, the world's simplest robot, which is just a point on a line that we can control the acceleration of. And as you hopefully recall, we can write this in state space form as x dot is this A matrix, 0, 1, 0, 0, x, plus a B matrix that's 0, 1, and then the output is 1, 0, x. This means that the output is the position of the point mass, and x1, the first component of x is the position, the second component of x is the velocity, and then u immediately gives us the acceleration. So now our job is to somehow connect y to u, meaning pick our input in such a way that this system behaves. And in fact, here's an idea. We want to drive the system to 0, which means stabilize it. So why don't we move towards the origin, meaning the position of the robot is what it is. And let's say that here is the origin. And our job is to drive it to the origin. So if the position is negative, meaning we're on the left on the origin, we should probably move in this direction. If the robot is over here, we should move it to the left, which is in a negative direction. So that's a very, very simple idea. And in fact, if we turn this into math, we see that if y is negative, so y negative again corresponds to if the origin is here, us being on this side, then u should be positive, which means move in this direction. And similarly, if y is positive, then u should be negative. And here's a suggestion, right? Let's pick the world's simplest controller that achieves this. Simply the negative of y. So y positive means negative u, y negative means positive u. So let's try this and see what it actually does. And what we need to do first is understand how does this change the system dynamics. Because what we really did now is we had u equal to, well, we had minus y, so k in our example was just a 1. But in general, k here could be some more rich structure. And if u's and y's are multidimensional, then this needs to be a vector. Now, we know that y is equal to c times x, so we can write this as u being equal to negative kcx. So now let's plug this into our differential equation that we have. So x dot is ax plus bu, and now instead of u, we're plugging in this term, right? So then we get a minus bkcx, or if we plug everything together, we get a minus bkcx. And this we can write, if we want to, as a hat times x. So this is just a new system matrix. And of course, our job is to pick k now, so that's the real part of the eigenvalues of a hat is strictly negative. Or in other words, pick, if possible, k such that the real part of lambda is strictly negative for all lambda that is an eigenvalue to this new system matrix a minus bkc. So that's really our job here. And we've, in a way, already picked k. We said k was equal to 1. Well, let's see what's happening if that's the case. Then we have x dot is, this is a, this is b, this is k, and this is c. So this is what we have in terms of the system matrix for our robot. And one thing to note, first of all, that 1 times 1, 0 is just 1, 0. And if I multiply this by 0, 1, then I get, what do I get? I get 0 times 1, then 0 times 0, 1 times 1, and 0 times 1. So this is what this whole expression is equal to. So now I can just take this matrix and subtract away this matrix to get the right answer. And if I do that, I get x dot is 0, 1, negative 1, 0x. And this is for my particular choice of k. And let's check out what the eigenvalues are of this thing. Well, you write eig in MATLAB and you get the answer. Or, as we will see in future lectures, you can actually compute it and say something about the clever choice of k in that way. But for now, we're just going to immediately plug this into our favorite software system, and we find out that the eigenvalues are plus and minus j, where j is square root of negative 1. So is this system asymptotically stable? Well, the real part of lambda for both lambdas, so we have 2 lambdas, the real part is 0 because this is a purely imaginary system. And as I said last time, if I have 2 imaginary eigenvalues and all the others are well behaved, in this case I don't have any others, then I have a critically stable system. And in fact, since I have imaginary components, we've already hinted at this, that what we actually end up with are oscillations. So this is a critically stable system. And if I simulate what this robot is doing, it's going to look like this. Wow, wow. Really what's happening is this thing is just going back and forth, back and forth. So what's the problem? We clearly did not stabilize it. We know it's not asymptotically stable. In fact, it's just going back and forth, back and forth. Well, here's the problem. When the robot is, let's say, on its way away from the origin, then we're pushing it, correctly so, towards the origin. But when it's on its way back, we're still pushing it equally hard, even though it's actually going there almost by itself. So we're kind of not taking the direction in which the robot is going into account. What this actually means is that we're not looking at the velocity, because the velocity is going to tell you which direction it's going in. So the problem is that we do not take velocity into account. And remember what the state is? The state is position and velocity. So the problem is that we need all of it typically to stabilize it. We need the full state information, not just the output. So output feedback directly like this doesn't quite work. But instead, we want to operate on x instead of y. But here, of course, is the problem. How do we do that? And the corollary to that is, we don't even know x, we only know y. How in the world can we design controllers for things that we don't know? Well, as we will see in the next module, it's possible to figure out x from y a lot of times. If you just think of y in this case as being the position, and x being y and as x being position and velocity, then velocity, right, we can get by measuring 2 positions after each other and dividing it by the time in between the measurements, then we get an estimate of velocity. So it's clearly possible in this case to at least get an estimate of the state from the output. So like I said, this is the next module, but in the next lecture, which is the last lecture of this module, we'll pretend that we actually have x and revisit the world's simplest robot and see how can we actually stabilize it if we have all of x and not just y.